Good morning. It's 10 o'clock now in Taiwan, and I think that in most of the places in Asia also morning. And welcome you to this webinar series. The idea came up some times ago. I forgot exactly when, but I think the idea is that firstly, this is a planned by the strong earthquake working group of RAC of the AOGS Regional Advisory Committee. And the chair is Professor Fuqin Huang, and she will say a few words afterward later on. But I want to mention just that because for regular AOGS meeting every year, we have very good talks, but they're always very short because of regulation, only 15 minutes or so. So I thought that there should be some more lengthy, more detailed, reviewed kind of lectures, since it could not be added to the program at the AOGS annual meeting. So maybe we could do it online for one thing. And secondly, that you can see that the speakers today and maybe in future will all be eminent scientists in the special areas. So I think that the lectures, perhaps we could, with the agreement, we could kind of summarize or compile them into a lecture notes, and to be published later on. So that is a kind of thinking behind this series. But I can see that President Takehiko Sato, he's the president of AOGS, he's online. Maybe I would like to invite him to say a few words to all of us. Takehiko, please.
Yes, thank you, Win-san. I'm Takehiko Sato, current president of AOGS, and I'm very glad that strong earthquake working group of regional advisory committee is now having an excellent seminar today. And as you see the program, we have good speakers, Japanese speakers. So this is going to be a very good preparation for you to come to Japan for AOGS 2026 annual conference in Fukuoka. As you know, almost every week, we Japanese have earthquakes, something like a magnitude 6 point something, and in different parts of Japan. So maybe you will receive more useful information and also knowledge from excellent speakers today through the seminar, online seminars. Thank you, and please enjoy the seminar. I will hand the microphone over to Fuchon.
Yes, thank you very much, Takehiko.
Okay, it's very nice to see you here. It's our first online webinar, online meeting about the Sichuan earthquake from long-term risk assessment to the short-term observation techniques. Today, I think it's very interesting for the topic. Okay, please, next. Okay, today we want to talk about 3 points. Why we should have strong earthquake group for AOGS Regional Advisory Committee. And then, what is the strong working group? And what is the topic? And who are the speakers today for the webinar? First webinar. Okay, the next. And from this group, from this map, we can see the distribution of strong earthquakes with magnitude more than 7 global view since 90,000. And the earthquake is very active since 1900 to 2024. why. The next. Hi, Mengqi. Please press the button. Yes. Okay. Several hypotheses to explain. The monitoring techniques, maybe based on the development of science and technology, we cannot get more or the whole catalogs of the earthquake in the past. And the second point is human activities for the sake of increase in population for the time of 1900, and also global climate changes. But which one is the appropriate one? Okay, the next. Now, this map is the magnitude from 2023 to 2024, the beginning of 2024. The map shows that the earthquake in the next button. Yeah, the distribution of earthquake mainly along the 30th tectonic belt. And what is the short-term prediction for the earthquake? But we cannot do, even present time, we cannot do the prediction in short term, in exactly or in accurate. But we must not stay still and wait for the for the current situation. Okay, the next. Yeah. And from this figure, this map shows that the earthquakes with magnitude more than 7 from 2024, the location of the earthquake changed, distributed from 30th tectonic belt to Pan-Pacific belt. The main places changed from land collection zone to subduction collection zone, many to the subduction zones. So especially the Japan, the earthquake in Japan is more active than before. So to organize a group of strong earthquake under the umbrella of AOGS, right? The members, we can do something for the situation, maybe. So to carry out some works via online seminar and online discussions and webinars is appropriate approaches. So that's why we try to have a strong working group. Okay, the next. Now AOGS Regional Advisory Committee has 4 groups. Strong earthquake is one of them. Okay, the next. Okay, this is the members. The right figures show the members from the 2 last years. And then we have done what we are doing. We are doing online seminars, earthquake monitoring, modeling, and socio-dynamic models, and also online discussions on emerging issues, anomalous phenomena related to recent big earthquakes. And what we have done since August 2024, 4 online seminars, and 1 online conference on Myanmar earthquake. And what will be arranged? More online seminars and 1 more online discussions. Our webinar is today, the next great one. Okay. Our mission, first, to bring together members of the scientific community to exchange ideas. First, to design activities focus on exchanging information. Okay. The next, to promote regional cooperation on scientific projects. Okay. To improve in educating and reaching out the public. Okay. The next, our charter. The next, to exchange ideas on earthquake and scientific challenges. For example, today's webinar, we will change the newly built the ideas and newly built observation techniques for imminent earthquake precursors. Okay, the next, to enhance understanding the nature of earthquake process from preparation to faulting. Okay. And to promote the regional and international cooperation on scientific challenges relevant to Sichuan earthquake and other natural events to prevent and reduce disasters. Okay, the next. And our activities to continuously pattern. It's online seminar and sessions for AOGS. Okay. Yes, for international research projects, try to organize some bilateral cooperation frameworks of the project proposals. Okay, the next. Our scientific disciplinary is widely involved. Observation and monitoring, okay, and physical models and simulation. That's the list. And petrophysics and rock fluids interaction. Okay, the next. And risk assessment and earthquake predictability. Even though the resilience of the mega cities. Okay, the next. And we also want to more scientists to join us for the observation techniques and monitoring networks. And okay, next. And the geodynamic simulations. The next. Link between the multidisciplinary observations anomalies and the earthquake process, aiming at searching for effective approaches to improve short-term prediction efficiency. Okay, the next. And we also want to have the rapid information collection and assessment of disaster right after strong earthquakes to serve for rescue and disaster mitigation. So it's very useful for the current situations of global changes and the situation of earthquakes in subduction zones. Okay, please contact at present is 3 emails, and we have the online seminars already. The first is from satellite. Japan channel have specific satellite for earthquake precursors of electromagnetic. And also we asked the professors to give us the newly observations in geochemistry, very cheap and very easy ways. The objective for the observation tactics is focusing to prediction. It's a very more easy way to get the information. Okay, the next. And also we asked Dr. Wang Hui to give us the lectures on geodynamic modeling, the process of rupturing, and then the professors from physics to get the physical models of the earthquake process. Okay, then next. And the conference on Myanmar earthquake, the first anniversary, is a very interesting and very important to give us ideas. The next button. And lessons learned from this conference. Coding system of zoning map. Coding system of zoning map for construction, for better construction, for safer construction, need to be modified after strong earthquakes, not only in Myanmar, but also in Thailand and other countries nearby. The source of earthquake is limited to borders, but the disasters induced by earthquake, and so very few very important disaster information collection right after earthquake is more important and useful for rescue. I get ideas from this conference, and very few precursors were discussed. That means prediction with precursors for disaster mitigation has a long way to go. But early warning doesn't. Observation techniques for early warning system have been available in China and in Japan, and also in other countries and regions. The observation techniques, advanced observation techniques, is already available. So we have techniques to get the observation system of early warning system to get the first step. Maybe and then we can have a second or the in the future to get more precisely earthquake prediction. Yes. So the project or the proposal need global view and international cooperation. Okay, the next. So today we have the first webinar globally invited scientists, but later at last we got 3 famous scientists, Professor Kenji Satake, to show the Japanese statistic seismology, and Professor Chen Jiehong from Chengdu University to show the Liuli belt. Okay, so today's Liuli. The next. Yeah, okay. The next. Okay. Again the next. Why? Okay. So that's why we can get today's webinar. Our objectives to focus on the method for determining the next grade 1 along the global tectonic belts along from long-term to short-term. The next, Professor Kenji Sadaki will introduce the statistic method for the next grade one along the active force based on Japan test site. And Professor Chen Jae-hong will introduce his newly built advanced observation techniques for hunting short-term precursors. And Professor Aitaro Kato to introduce advanced data mining techniques. Is that right? I did not hear the PPTs or slides, so that's my ideas to show the topics for speakers. Okay, then after the presentations, we will have discussions. Okay, that's all for my introduction to this webinar and to the strong working groups. Now, I think I give the chairs and the times to speakers. Okay.
Yeah, thank you, Professor Huang.
Okay.
So we will begin the first talk to be given by Professor Kenji Satake. Kenji, are you ready?
Okay.
Yes, I'm ready. Can I
Okay.
share the screen? Okay, good.
Yeah.
Okay. Thank you. Thank you for inviting me. The title I was given is Earthquake Forecasting and Next Grade One, an experimental sites in Asia. But I'll mostly talk about in the case of Japan. So I just slightly changed the title. Okay. But I think most of the audience I know them, but just let me introduce myself. I'm Kenji Satake, and I got degrees here in Japan, and then after PhD, I went to Caltech and University of Michigan. Then I worked in Geological Survey, Japan. Then since 2008, I was a professor at Earthquake Research Institute, the University of Tokyo. Then 2024, 2 years ago, I was retired. Then now I am at the National Central University in Taiwan. I served as a IUGG chair of Joint Tsunami Commission, or also YASPE president. And in AOGS, I was a SE Solido section president and also AOGS president some time ago. And for the government, Japanese government, I work as a member of the earthquake. Yeah, actually, I'm a chair of the long-term evaluation committee of earthquake research committee. I'll introduce later, and also a member of the Central Disaster Management Committee of Japanese government. So that's from my academic experience and also like a governmental service. I'll talk about the situation in Japan now. So today's topic, first I like to define the prediction and forecast. Then I'll talk about history of earthquakes and prediction forecast research in Japan, following these major earthquakes in Japan. Then I'll introduce you the current implementation of long-term forecast of Earthquake Research Committee and a subsequent earthquake advisory that has been implemented in the last several years and now in effect. Okay. So first, in seismology, prediction refers to the deterministic and short-term, usually defined as like hours to days or in short time scale. And it is currently considered as difficult, and at least it's not practical yet. Okay. Whereas forecast refers to probabilistic and intermediate term to long term. That means days to weeks or even years or decades time scale. And so as I show you later, this forecast is currently operationally implemented. And for the prediction, there's some non-scientific, I would say, prediction. And that was kind of well, it's not issued, but happened in the topic in the last year, about a year ago. There's a rumor that the major earthquake would take place in Japan in July last year. And that led to a drop of visitors from Hong Kong or South Korea, or even from Taiwan to Japan, where the false alarm was practically widespread. So you can see then how did they hear the rumor about possible earthquake? Many people heard from the news media or video or Instagram. So like these SNS spread it such a non-scientific prediction, and that affected the visitors or tourists to Japan. But this one is not really scientific one. But for the scientific or just to review the forecast, the prediction, and warning. This is time scale. There's an earthquake here happened. Let me see just okay. Here's an earthquake. Okay, and as I said, the time scale is like a long term, like a century to decades or years. Then midterm is maybe weeks to days. And short time is like a days to hours. Okay. So long term is probabilistic evaluation or long term forecast, and that is basically based on the past history of the recurrence of earthquakes. And midterm, like still probabilistic evaluation, with weeks to days, and that is based on seismicity. And I'll show you later that currently the Nankai trough earthquake information or Hokkaido Sanriku subsequent earthquake advisory are in effect implemented based on midterm evaluation. Whereas short-term prediction, these are mostly based on the precursors, and it's currently considered as impossible. But as Fuchin said, there's an earthquake early warning system is implemented, and that is not really forecast or prediction. That was after the earthquake, or I should say like a fault motion occurred, then the information of the earthquake itself is relayed earlier than seismic waves or earlier than tsunami waves. So this earthquake early warning or tsunami warning was issued after the occurrence of earthquake or fault motion. So it's not really the forecast or prediction. So currently in Japan, Japan Meteorological Agency, JMA, is responsible for earthquake or tsunami information. So this is just implemented current time scale. And again, when earthquake happened, first earthquake early warning is issued. So that is that again, the idea is try to disseminate the information before the seismic wave or ground shaking starts, right? So the time scale is like several seconds. And so this may or may not arrive, this information arrive the people before the ground shaking. Then typically like 1 minute or 1 to 2 minutes, the seismic intensity information, which part of failed earthquake is issued. So this is seismic intensity information is basically the intensity distribution without information about earthquake source or magnitude. Then within like 3 minutes, they locate the earthquake, that is location, depth, and magnitude. Then based on that information, they judge if that can be a tsunami or not. So the tsunami warning or advisory is issued within like 3 minutes. Then around 5 minutes, 5 minutes, you get more information about the earthquake, like a CMT, like a focal mechanism or moment, or the seismic moment. Then after, if the tsunami warning is issued or advisory issued, then they confirm the tsunami is if tsunami is really happened or not. Okay. So then tsunami may be a tsunami warning or advisory may be cleared in like hours or maybe days if in case of very large earthquake like a Tohoku earthquake. Then after that, I'll show you that as I said, I'll talk about the subsequent earthquake information will be issued And that is usually for one, not usually, it's issued for 1 week. Okay. So this is like a time scale after the earthquake with official information from JMA. So let me talk about some history about earthquakes in Japan. In 1891, there was a big earthquake, inland earthquake, Nobi earthquake, with magnitude about 8.8, and in inland near Nagoya, and this fault appears. And this caused about 7,000 casualties. So after that, Imperial Earthquake Investigation Committee was formed by in Japanese government. The objective of this committee was to investigate first whether there are any means of predicting earthquakes. Or the second one is what can be done to reduce the disastrous effect of earthquakes. So you can see that this objectives is very similar to what the Huchen said for this particular, the commission of this AOGS. And then the work of the committee may be classified into like 5 different fields, like a statistical method, instrumental observation, geological investigation, and physical studies about earthquake source, and some practical the method to reach these objectives. Then in this, under this committee, Imperial Earthquake Investigation Committee, the 2 famous seismologists are very active. First one is Professor Omori, Sakichi Omori, and he is known for this inventing this the Omori famous Omori law of the number of aftershocks is just decaying. Another person is Professor Imamura, and he's both Omori and Imamura invented some seismograph system, but also Imamura made the long-term forecast of earthquake based on historical recurrence. In 1905, he said there will be a large earthquake in Tokyo in the next 50 years. While Professor Omori criticized that it's just Imamura's kind of forecast caused some, the people were worried about it, and then just he really criticized about this forecast. But then the forecast, then after 20 some years, almost 20 years after this forecast, the Kanto earthquake actually happened in 1923, as I show you later. But then also he forecasted, Imamura forecasted the Nankai Trough earthquake about 1930, and then a large earthquake occurred in 1944 and 46. So as I said, in 1923, there was an earthquake in Kanto area in Tokyo. And this is almost magnitude 7.9, and caused more than 100,000 casualties, mostly from fire in Tokyo and Yokohama. So after this earthquake, the Imperial Earthquake Investigation Commission was renewed, and the Earthquake Research Institute, where I used to work, was established in 1925. So last year was like 100th anniversary of ERI last year. Then in more, I just skipped some details, but it's just say in 1960s, the earthquake prediction project started in Japan. And that also started from the earthquake prediction so-called blueprint was published in 1962. That proposed various measurements such as cluster deformation, sea level change, seismicity, seismic velocity change, active force, and geomagnetism. Then the nationwide earthquake prediction project, each one is 5-year term, started in 1965. Then like a coordination committee for earthquake prediction is a committee has been is established, and this has been held even now since 1969. Currently, this committee exchanges information on the observation and research and held for 4 times a year. So under this prediction project, several areas in Japan are identified as areas of investment intensive observation or spatial observation. And intensive observation area include Kanto and Tokai areas. Then around that time, 1960s or 70s, there are seismic gaps has been identified. First, like Professor Utsu pointed out, there's a seismic gap in Muroki in Hokkaido, where many large earthquakes happened, but this Muroki has been gapped. Then he pointed out in 1972, then in following year, magnitude 7.4 earthquake happened. And in Tokai area, along Nankai Trough, there was an earthquake in 1707, Hoei, 1854, 2 earthquakes, Tokai and Nankai. But then in 1944 and 46, as Professor Imamura forecasted, there are 2 earthquakes happened. But Ishibashi in 1977 pointed out this Tokai gap, eastern end of this Nankai Trough, is a gap where the earthquake happened the rupture extended in 1854, but not in the 20th century, 1940s. So there's a seismic gap. And then he forecasted that there will be a Suruga Bay earthquake or Tokai earthquake happen. He said could happen anytime. But it never happened since about almost 50 years since his forecast or prediction, but it's never happened so far. And also there has been some precursory cluster deformation as been reported. One is like a Nankai earthquake, Tonankai Nankai earthquake, and in particular for the Tonankai earthquake in the eastern part, happened in 1944. Just before this, there was some precursory cluster deformation before this earthquake happened. However, this has been questioned by more recent studies. And also in 1964, there was an earthquake in Niigata Prefecture. It's Niigata earthquake. And also before this earthquake, there was some precursory cluster deformation happened. That is pointed out. But again, this is later. This phenomenon is also discarded by the later study. So these precursory phenomena are now considered as not true. But then, because of the reported precursor and pointed out the Tokai gap, there's a council for Tokai earthquake prediction was formed in 1979. So the 6 seismologists composed a council to advise the Director General of JMA, and eventually the warning will be issued by Prime Minister of Japan if such a precursor is found. However, this has been established in 1979 and worked until recently, but it was judged recently that the short-term or deterministic earthquake prediction is currently difficult based on precursor. So this council was terminated in 2017. So the same council still monitors, well, not same, but it's the same members, the similar council still monitors activity along the Nankai Trough, but they just gave up for the short-term prediction for the Tokai earthquake. Then in 1995, there was an earthquake in Kobe. That is also near Kobe, near Osaka. And that is 7.3 and caused about 6,000 casualties. So after this earthquake, the headquarters of Earthquake Research Promotion is established in Japanese government. And then there are 2 committees. One is policy committees. They just discuss or assign the budget. The other one is Earthquake Research Committee. They basically meet every month to evaluate seismic activity in Japan. So the Earthquake Research Committee also make long-term forecast. Shown here in the left is like a long-term forecast for the subduction zones. So Kuril Trench, Japan Trench, and Nankai Trough, and Ryukyu Trench, they just make a forecast of the large, they examine the past history of large earthquakes, and based on that, I'll explain this later, but just based on that, they just make a forecast. Then, based on this forecast of subduction zone and inland active earthquakes, they make the National Seismic Hazard Map that indicates the probability of ground shaking And for example, this one is just show the darkest color indicates the highest probability, and then the orange and yellow probability of like a magnitude, sorry, the intensity of 6 or in the next 30 years. But for the long-term forecast, it was made not only for the subduction zone, but also the inland active faults, where for which the 30-year probability is pretty low compared to the subduction zone. And although this earthquake research committee makes such maps, but there are some criticisms, like most famous one is Bob Geller, and then he just criticized after the Tohoku earthquake, that many earthquakes have occurred in low probability region of the previous map, which is shown in the lighter color. So he really criticized that the seismic hazard, this national seismic hazard map is useless based on the recent earthquake occurrence. But anyway, for the earthquake recurrence, the long-term forecast is based on the earthquake recurrence pattern. So earthquake recurrence could be periodic in time or random. If it's random, we call it Poisson process. And either periodic or random, we can see that we can plot the time interval between earthquake and the horizontal axis and the frequency in vertical axis. So if the earthquake is periodic, it has the peak, right? The frequency has a peak at average interval, average time. And that can be modeled by statistical distribution like log normal or gamma or whatever, the probability density function. If earthquake is totally random, a Poisson process, you still can see draw a diagram like this, but there's no particular peak because the shorter interval has more frequent than the longer interval. So it's just an exponential function like this. So once you model this earthquake interval with such a statistical functions, then we can calculate for example, if the average is 100 years and now is like 50 years since the last event, then the next probability for the next 30 years will be like the area of A over A plus B, right? So this is just how we calculate the probability of the next earthquake. Again, this depends on the statistical function. If this is just periodic, then earthquake, the probability will increase, right? Soon after the earthquake, probability is low, but toward the next earthquake, the probability will increase. Whereas if this is totally random, like a Poisson process, the probability will be constant. It's time independent. Yeah. So using this method, we can make a forecast for the earthquake. For example, along Nankai Trough, we know that earthquake has repeated after this approximately 90 to 150 interval. How do we know such an old earthquake? We have many historical documents. And modern and historical documents, the typical characteristic of Nankai earthquake is like a ground shaking in Western Japan. And also, particularly, that was recorded in Western Kyoto or Osaka, Nara, because the old capital was there. And some the cluster deformation, subsidence of Kochi plain or uplift of this peninsula. Or typical thing, interesting thing is the stop. This Nankai earthquake stops some hot springs, and that has been recorded in historical document, and also some tsunami damage. So if these are found in historical documents, we can identify the Nankai earthquake. And we know that happened about 100 or so year interval. So based on this time, we can just make a forecast or long-term probability can be computed. And first forecast was issued in 2001. And that time, we just separate Tokai, Tonankai, and Nankai earthquakes, two different earthquakes. But in 2013, after Tohoku earthquake, we revised. And then we just consider that earthquakes are not only for these two types, but there's a various, the types of earthquake can happen. So it says size will be somewhere between 8 and 9, and then we calculated the 30-year probability based on the recurrence. But those are based on the probability from it's a BPT. Sorry, I didn't explain this one. One of this is called BPT, is the Brownian passage time. It's basically similar to log normal distribution. But if you use this BPT, and then depends on which earthquake, which of the past data set we used. You use only the 3 most recent ones or longer one, because you can notice that for the older earthquake has a longer interval. That may be due to missing data. So depending on which data set we use, you have a difference. But in either case, the probability increase, but it's not as large as in whatever the method you use, the probability is still less than 40%. I mean, 30-year probability is less than 40%. However, for this earthquake in Nankai Trough, there has been some papers pointing out that this recurrence is not really strictly periodic. That means not all earthquakes recurrence is not same and size is not always the same. Okay. So we call it if recurrence is the same and magnitude is same, we call this characteristic earthquake. But the reality is sometimes earthquake is large, sometimes earthquake is small, and recurrence is large, longer or shorter. So this is called a time predictable or predictable. And if we introduce this, for example, here in Nankai Trough, we have some uplift event in here in Muroto Peninsula. So this uplift event uplift amount is large in 1707 and somewhat in smaller in 1844, 1854, and also 1946. So if you consider the difference in this uplift amount, we can use the so-called time predictable model. And based on this time predictable model, the next one will be predicted as 2032. And using this, we can still estimate the probability for the next 30 years. And that is adopted in 2014. And then there's 60 to 70%. But now is, as of last year, that's increased as high as 80%. And that has been known to in Japan. But more recently, that means last year, we revised this long-term forecast. And so far, we used either BPT, characteristic earthquake model, the characteristic earthquake model or time predictable model. But if we allowed some disturbance, this is called BPT or slip size dependent BPT. So they are more probabilistic models. So this one is newly proposed. So we adopted 2 different kinds of models. One is BPT, and then based on this, the 30-year probability is 20 to 50%. Whereas if we adopt this slip size dependent BPT, that will be 60 to 90 plus percent. So we published these 2 different numbers last year. So that's about the long term. But now, as I said, well, the pattern is not always the same. For example, in 1944, eastern part earthquake happened. In 2 years later, western part ruptured. 1854, like 2 days apart. Okay? So if we have earthquake in eastern part, for example, then there will be the past record indicates that the western part ruptured in 2 days or 2 years later. Right? So that means if earthquake happened for example, in eastern part, then the possibility of earthquake in the western part will increase. So based on this, we introduced the Nankai Trough earthquake information that is categorized like, first we say under analysis, then megathrust earthquake alert. That is, if earthquake of magnitude 8 happen in the eastern or western part, then another earthquake may happen, another similar earthquake may happen. So it's a megathrust earthquake alert. And if smaller earthquake, like a magnitude 7 earthquake happen somewhere along this Nankai Trough, or unusual slow slip, that is like considered as precursor at the plate boundary happens, then there will be the possibility still increase. So the megathrust earthquake attention is issued. So this system has been in operation since 2019. Then the first information that means this one, is issued on 2023 in August, following the Hyuga earthquake of magnitude 7.1. Because if magnitude 7 earthquake happened, then this will be issued. So this is Nankai Trough, but also we have similar subsequent earthquake advisory for the Hokkaido to Sanriku region on Japan Kuril Trench and Japan Trench, because this is based on the fact that you may remember that 2011 there was a magnitude 9 earthquake happened, and that caused the almost 20,000 casualties. But 2 days before this earthquake, there was a magnitude 7.3 earthquake that can be considered as washout. On Kuril Trench, there was a 1963, there was an 8.5 earthquake. But 2 days before, again, there was another magnitude 7 earthquake. Not along this continuation of this, we have a Kamchatka earthquake that happened last year. And that was like about 10 days before the magnitude 8.8 event, there was a magnitude 7 earthquake happened. So there's a possibility that if large earthquake happen, or like a magnitude 7 earthquake happen, the possibility or probability of the subsequent earthquake is increased. So statistically speaking, if the magnitude 7 or larger happen in there, if you look at the catalog of the Japan, all over the world, then there's actually the 1,500 cases of magnitude 7 earthquake. Among them, 19 cases, which is about only 1%, in case another larger earthquake happened within 1 week. So, but you see, 1% is very small, but for the irregular probability at the ordinary time, the probability is about 1 week probability about 0.1%. So compared to 0.1%, 1% is about 10 times larger. So that's why we just issue the subsequent earthquake advisory. And this has been implemented in 2022 in December. Since then, there are 2 times there's issued, twice actually last year. Last year, December, the first time. Then this year, in April, the second time, this advisory was issued because magnitude 7 earthquake happened. But magnitude 7 earthquake in this region is not very unrare. And statistically speaking, about 2 or 3 years, once in 2.3 years, the magnitude 7 earthquake. That means this advisory will be issued almost every 2 years. Although last year and this year was the first cases. So to summarize, in Japan, the past destructive earthquakes have changed academic and government systems for earthquake research, including prediction and forecast. And short-term deterministic prediction is currently considered difficult. And long-term probabilistic forecast is in operation. In Japan, long-term forecasts of large earthquake for the next 30 years have been announced for subduction zones and inland active faults. When a large earthquake magnitude larger than 7 occurs along Nankai Trough or Japan Kuril Trench, then probability of larger event, that is 8 or larger, increases, and advisory of subsequent earthquake is issued. So that's all. Thank you.
So thank you very much, Satake-san. Any questions? We have time. For questions to Professor Satake. But let me ask the first question, because you talk about there's a map for probability of earthquakes, right? However, the most frequent earthquakes happen the other side. Are these small earthquakes or what? I mean, there could be difference in many.
Let me see.
In this one, yeah.
You still see this one?
Yeah, right.
Oh, okay. I wasn't sure. Well, actually, this one is the right-hand side is just a damaging earthquake. So that's this is more like a damaging earthquake. That necessarily means the earthquake size, I mean magnitude. But he plotted, I think, the damage. The number in parentheses is a casualty. I think it's casualty. Yeah, casualties. So damaging earthquake and size of earthquake may not, damaging earthquake and ground shaking may not be always the same, right? Usually it's proportional, but it's not exactly the same. So that's one thing. And yeah, and also the comparing here is epicenter. The shown here is the epicenter of the earthquake, whereas the map shows the ground shaking amount. So it's not exactly the same thing, but it's, well, yeah. Okay.
So, other questions?
Yes, I have one.
Yeah, please,
Oh, hi.
Okay. Yes. Actually, I have two questions. One is for AOGS RAC. Because this talk, I have to say thanks for Professor Kenji Satake. It's a wonderful talk. So I think my students and the future students in my lab can benefit from this presentation. So I wonder when or where can I download the recording of this talk? This is the first question for AOGS. And the second question is I learned a lot useful method and information from Japan's policy and strategy to the tsunami forecasting and prevention. So I have a very general question for Professor Satake. In terms of in Taiwan, what should we do, or what should we focus on for the tsunami warning or forecasting?
Well, first question I cannot answer. I think the Fuchin or somebody will answer. Yeah.
Yeah.
Actually, I'm not sure if this is recorded or not. If it's recorded, I'm fine with sharing this. And for the second question, you can see this. This is the current system in JMA. But I think that basically the Taiwan same thing can be done, or is being done. Actually, we have earthquake early warnings, right? And for the tsunami. Yes. Well, the near field, I'm not sure if the system is implemented, but it's basically what they do is based on the seismic information. They just judge the possibility of tsunami. So the same thing can be done for either near field or also the far field tsunami that may affect Taiwan.
And other question, comment. I mean, okay, to answer Professor Wu's first question, I think that we should be able to publish the video, I mean, on the web page, or even put it on the YouTube between 1 to 2 weeks time.
YouTube. Yeah. Okay. Yeah.
I hope that is quick enough.
Thank you very much. Yes.
Yeah. And maybe I see Professor Guofeng Ma老师你在吗？
我在.
Yeah, you have a question to Kenji, or you talk to him?
Well, that's a great talk. Yeah, well, I do have some, I don't know, with the question of comments or in between, because Kenji actually gave a wonderful talk for very, very structured an idea about the concept of earthquake prediction or precursors and the long-term forecasting. I just come back to the very first question Professor Ip asked about that low probability, but higher earthquake occurrence. So Kenji, did you mind to share again that figure earlier? That national hazard map with damaged earthquakes, mostly in the Western, but because, right. I want to mention that actually Taiwan, Japan, New Zealand, we have earthquake hazard trilateral meetings for 15 years already, since 2010 actually. So this one was after 2011, we discussed about why in Japan, many damaged earthquakes occur in a low probability region. And that's also, again, for this map, it was a forecasting for next 30 years. But in the other way is for very large earthquake, it might not be presented in this map because recurrence interval may be 1,000 years, which doesn't count in this map. So I think after that, we'll have some discussion on this matter. If we come back to Taiwan, we also discuss what that happened in Taiwan, like our hazard map show like negative proportional to the occurrence of large earthquakes. But in Taiwan, actually, our recurrence interval is like every 300 years in general. So far, our map can actually reflect to occurrence of recent large earthquakes. So just to address the question to Professor Ip first. And then for what Jordan was saying, but I think that's what we are doing as well. Like Kenji was saying, in Taiwan, we do have similar patterns for the hazard map for early warning, but the short-term forecasting one still not clear because I was also not confident to that level yet. So that part we didn't really make that as a routine or exercise in our system. So that's somehow my comments to the questions earlier. However, I have another comment and question actually. Kenji, can you share this GPS statistic thing? I've been thinking, or maybe Kato-san is online, then he might give some idea as well. Remember that earthquake from GPS, you see the statistic of repeating earthquakes.
GPS?
Either GPS or accumulation of the slip. Like the.
Oh, you mean this one?
Yeah, right. Yeah, that figure, yes.
Yeah, okay.
Because now we've been looking at the fiber data, and for the Miron 4, for example, we actually see a lot of interseismic behavior.
Oh, yeah, right.
Which was not yet really counted for this model, because this model was established maybe in 80s or 90s.
Yeah, that's true. Yeah, that's true. This is 1980s. Yeah, right. So right.
So my question is whether we are able to somehow modify this model from now the observation for like 20 years, or now for fiber data, we might have more interseismic observation for the fault response to neighboring earthquakes and justify this. I
don't know that, as I said, for like such a slow slip is considered as maybe an unusual slow slip may be considered as a precursor for the large earthquake, but I don't think this is is counted for like interseismic period movement. But you're right. Well, that's really depends on the coupling rate, right? If, for example, the subduction zone earthquake, sometimes we compare this recurrence interval and typical slip amount and with the convergence rate. That is that if the coupling is like 100%, then that means it's totally coupled and only moved at the time of the earthquake. But if the coupling rate is low, that means you have some intermediate interseismic movement. So in a sense, we just consider this in terms of the coupling rate, I think.
Yeah, thank you very much.
I think time's up for one thing, but secondly, we are planning the next webinar. So I think the Professor Ma, you'll be invited. Yeah, you will come back and ask all the questions.
Yeah, actually, I have to leave for my student school meeting because I didn't know the time of this webinar until like a week ago. So sorry for the conflict of time, but happy to join for the first hour, but sorry to miss other 2 talks, but I will catch up.
So the next one will be given by Professor Zhihong Chen. Professor Chen, are you ready?
Yes, I'm ready.
Great.
Okay, great. Thank you for the invitation. Today I want to show the space-based high technology for hunting the earthquake precursor. And here is the outline. The first is the motivations, and the second is the we built a novel observation systems named the monitoring vibration perturbation in the lithosphere, atmosphere, and ionosphere. MEP LAI system to monitoring the wave propagate from the lithosphere to the ionosphere. And at the third part of the talk is now we have we try to achieve the terrestrial sphere 4-dimension project, and I will show later. And finally, I will told you how to hunt the earthquake. There are 2 very important questions. The first one is, why do we need space-based technology for earthquake detection? Because most of the instrument was installed in the continental place. So that means if we want to predict earthquake global, it's very difficult because most area in the Earth is the ocean. So the space-based technology is very important. But why till today is still a great challenge? Because we didn't fully understood the coupling between the lithosphere to the ionosphere. So that means we need a novel observation system to understand the core mechanism of the interaction between the lithosphere and the ionosphere. So this figure was proposed by the Hayakawa in 2016. So you can see from before the earthquake, from the lithosphere to the ionosphere, they have 4 potential channels to achieve the interactions. For example, the first one, we know the radon gas would be released. That would change the content of the air, and that would change the ionosphere. The second one is the water level changes that will increase the conductivity, and the increase of conductivity would change the direction of the lightning that will hitting the ionosphere, and we will find an anomaly in the ionosphere. The third one is the acoustic gravity waves. Before the earthquake or failure of the material, the wave would be generated, such as the acoustic waves. So this kind of wave will propagate to the ionosphere and change the ionosphere. The fourth one is the electromagnetic wave emissions from the lithosphere to the ionosphere. But even we have this 4 potential mechanisms, however, the causal mechanism of the interaction is not totally understood. So that means a system for monitoring the vibration and the perturbation in the lithosphere, atmosphere, and ionosphere is emerging. So the first MBPI system was established in Lausanne, China. So here I want to introduce the first MBPI system. Okay, this is the location here, and that is very close to the Tibet Plateau. The famous in the things in Lausanne is the Buddha. So if you visit this place, you can visit Buddha here. Okay, this is southwest China. This is also the spicy place. So if you visit this place, you need to you can find many spicy food. Okay, you can see this is a system. This is the MBPI system. So in the left side, you can find that this is the eagle view. So many different instruments was installed in a very small area. So that means it is possible to monitoring the wave directly vertically propagate from the Earth's surface to the ionosphere. And in the right side, you can see we have I also list the instrument here. For example, you can see we have the parameter that were installed in the well, and we can monitor the water level changes because before the earthquake, the groundwater level will uplift or depression. We have 4 barometer and the thermometer in different altitude that can, before the earthquake, we have acoustic gravity wave that would be the source from the thermal changes. We have 2 broadband seismometer at the 2 corners. That means if the wave propagate, it is possible to detect the wave propagate, the elements of a wave propagation. We have 5 ground-based GNSS stations. At this station, we have 1, but we have the other 4 substations I will introduce later. We have magnetometer to monitoring magnetic field change near the surface, and that would also dominated by the ionospheric changes at the altitude of about 100 kilometers above the systems. So I don't want to introduce everything here, but if we integrate all the instruments together, it is possible to understand the coupling from the lithosphere to the ionosphere. That means it will be ranged between the near the surface to the altitude of about 350 kilometers. Okay, in China, we also have the CSES. That means the China Seismo Electromagnetic Satellite. If the satellite data integrated together, the upper bound of the monitoring range would be extended to 500 kilometers above the Earth's surface. So what we learn from this system? Okay, from this figure, I want to introduce the substations for the GNSS measurement. We have the geostationary satellite operated by the Beidou systems. So that means we can calculate the corresponding location and like Changxi and Yadu. That means we will have the TEC changes at the IPV point, which is right over the MBPI systems. So that helps us to monitoring the wave propagate from the Earth's surface right over vertically propagate from the lithosphere to the ionosphere. Okay, what we learn from this instrument? The first interesting thing is the loading earthquake. After we complete the establishment, the loading earthquake happened, and the station a distance between the loading earthquake and the MBPI system is about 100 kilometers. Before the earthquake, 3 hours before the earthquake, we can find the uplift and the depression in the Earth's surface. So you can see the bottom 2 figures, and then we also find the air pressure changes like this, and the radon. This is atmospheric electric field, and this is magnetic field and the TEC. So that means before the earthquake, it's possible to find the anomalies in multiple geophysical parameters. However, this kind of the leading time is just 3 hours. That is too short for practical applications. So that means we need to find some kind of precursor which is much time leading the earthquake occurrence. But this is also encourage us. And in 2022, I think the Tonga volcano eruption and the lava wave propagate globally 2 or 3 times. And here in this figure, you can see the red color. Red color is the air pressure. Blue, black, and the green color is the magnetic field. Orange color is the TEC record. If we only have the TEC record, this significant change would be considered to be dominated by the lambda wave. However, if we put all the instruments together, you can see the lambda wave is here. You can see the red color. Like this, we have 3 peaks. And a little later, you can see the 3 peaks can be observed in the magnetic field data. And you can also find the 3 small peaks in the TEC data. And the delay time is 10 minutes. So that means the acoustic wave could be successfully recorded by our MEPI systems. So this is also encourage us if before the earthquake, the acoustic can be generated, it would be detected by our systems. So this is also interesting. And this one is if the acoustic wave propagate from Earth's surface to the lithosphere, what can we observe in the magnetic field? Okay, this is Hualien earthquake in Taiwan. This is a high density measurement area. So you can see this is these three figures is the magnetic data. If the acoustic wave propagate to the ionosphere, you can see you have the chance to see the order of phase change in magnetic field, like these figures. So that means in the previous studies, many previous studies that shows the magnetic field shows the abnormal changes before the earthquake. That would be caused by the acoustic wave generated before the earthquake occurrence. So this is very and also very important observation result. Okay, this figure you can see what the acoustic wave propagate to what altitude the magnetic anomaly can be generated. That is also important. So in Taiwan, we are very lucky. We also have the Doppler sound systems. And you can see the yellow circle that is measured by the Doppler sound systems. And the blue curve is the modeling result. This is the time, this is the altitude. So you can see the red cross is the occurrence time of the magnetic field. That means this kind of anomaly is happen at an altitude of 100 kilometer in altitude. So that means if an acoustic wave propagate arrival the altitude of 100 kilometers, the magnetic field can be anomalous magnetic field can be found. So this is also very important. And after this, we are trying to develop the simulation result for this kind is the point source. This is plane source. So that would be help us to understand the interaction between the lithosphere to the ionosphere. Okay, what we have before the major earthquake, this is very important. Because we already have many different kind of data in different altitude. So before the major earthquake, we try to analyze this kind of data in time in the frequency domain. And this figure shows the ground velocity from the broadband seismometer, air pressure changes from the barometer, magnetic field from magnetometer, TC from ground-based GNS stations, ground-based GNS receivers. So you can see before the earthquake, all of the enhancement can be found a few days before the earthquake, and the enhancement will be happened at the 0.005 frequency hertz. So in frequency, so that means because this kind the multiple geophysical parameter they corresponding to different altitude, they share the same frequency. So that means the lithosphere, automosphere, resonance would be happened before the earthquake. This only obtained from the one stations that from the MEPI systems. So the interesting thing is if this kind of observation result can be observed from the spatial domain. So we try to collect the data in the spatial domain, and before the earthquake, this would be also encourage us. This is from the seismometer. You can see a little enhancement in ground vibration can be found here, but they're not so clear because in the lithosphere there are so many noise. It's difficult to easily to retrieve them. But the automosphere is a filter. So that means the signal within the limited frequency band, they will propagate to the high altitude. So from the magnetometer that reflect the change in the ionospheric current at the 100 kilometer, you can see a great circle here. red color, and the center of the circle is very close to the epicenter of the earthquake. Okay, the similar circle, red circle, can be also found in the TEC data. We named these kind of phenomena as seismo rainbows. Before the earthquake, the rainbow would be happen, and it is possible to be detected by the numerous ground-based instrument. So, is this kind of the anomalous phenomena can be used to predict earthquake? The answer would be yes, because before the Mado and the Yangbi earthquake, you can see the rainbow. This is the epicenter of the Mado, and the south part is the epicenter of the Yangbi. So in the north part, you can see the rainbow system associated with the Mado. In the south part, you can see the rainbow system associated with the Yangbi. Okay, it's not so clear. So it's also a challenge to separate the seismo rainbow system, because these two earthquakes occurred within one day. So that would be some difficult. But for the Menyuan earthquake, this earthquake with the magnitude 6.9, and you can see here the earthquake epicenter is here. So for the magnetic data, you can see the red distributed in very close to the epicenter, and you're surrounded by the blue and red. For the TEC, the central part is blue and surrounded by the red and the blue and red. So it's very clear. We try to predict earthquake by using the seismo rainbow. So this is the result. After the 2002, this you can see the formal earthquake prediction card here. Okay, also the Chinese word, but I think all of you can understood the word. And we predict the time and the earthquake magnitude, and the red point is the location. At the bottom, this is the receive. So that means if we submit the formal earthquake predict document to the China government, and we have this receive for approval. Before the 2022 Lusan earthquake, 2022 Markham, 2022 Luding, and the 2000 Jishan, we have successfully predict the earthquake occurrence. But for the successful and the permanent event is the Hualien earthquake. Okay, 1.5 months before the Hualien earthquake, we have this kind of anomalous phenomena. You can see the magnetic field anomaly and the TEC anomaly in the left figures. Because we only have the data in China, so we only have a part of the rainbow or a part of the circle. But based on the arc of the circle, it is possible to locate the potential epicenter of the forthcoming earthquake. So from the magnetic data, you can see the blue color, deep blue color, distributed in the eastern part of China, and we try to retrieve the arc of the blue color distribution and locate the potential epicenter by using this arc. And you can also see the red color from the TEC data, and we can also predict the location of the forthcoming earthquake by using the TEC data, and we have consistent result. So we wrote the formal earthquake prediction card, and this is the potential epicenter of the earthquake, and this is the prediction card. And we also have the receive. Okay, we have the good result. After 1.5 months later, the earthquake occurred. The time is correct. Location with the difference in location is only about 20 kilometer, and the magnitude would be the 0.5. So that is a very good result. For reason, we have tried to use some the filter or something and integrate the different different geophysical parameters. So, for example, this is 30 days before the Hokkaido earthquake. You can see the red color here, earthquake here, 30 days before. And 7 days before, we also have anomaly here, and the earthquake happened 7 days before. So that means we have seriously reduce the leading time. That means the reading time would be reduced from 2 months to a few days. Okay, you also find many circled here, so you can also check the USGS earthquake catalog, and the earthquake occurred in this area. So we will try to also release this kind of result in our website. And what is the next step of the MEPI assistance? The LERSAN was established in 2021, and now last year we also have the CHAOJA. That's about 200 kilometers away from the LERSAN stations. Okay, last week we have completed the third MEPI system in CHAOJA. CHAOJA MEPI system is the highest stations of the world. So I will also show you what we want to do. The next year we will have the other systems in Guangxi, so that will be helpful to understand the wave propagation even in the slight directions. Okay, this is the final. This is the image from our MEPI systems. So in this figure, we want to establish 3. And what will we have? Traditionally, we only have 1 point above the MEPI systems. So that is not enough. We want to have 5 horizontal plane for observation the wave propagate in the horizontal directions. So in the Earth's surface, we will put the magnetometer, we will put the broadband seismometer and the ground-based GNSS station. That will help us to understand the ground vibration and the surface deformation. For the second plane, at the altitude of 100 kilometers above the Earth's surface, the magnetic data will be used. For the 3 and 4, we will the Doppler sound system will be conducted. Currently, the 2 or 3 frequency was transmitted by the transmitters. So that means it's possible to observe the 2 different the wave propagated in 2 different altitude. Note that the EM signal transmitted by the transmitter will be received by the more than 6 receivers. So that means at this kind of altitude, at each altitude, we will have more than 6 refraction point. So if this, you can image that it's like a seismometer hanging in particular in the atmosphere. So it is possible to detect the wave propagate in the horizontal plane. Okay, for the upper bound, we will take the TEC observation from the ground-based GNSS stations. So that means if we complete the MEPI systems, we will have 4 different observation altitude. That would help us to monitor the wave propagate in the slight directions. Okay, you can also see these images. And currently, we already have LERSAN, CHAOJA, and the Dalton MEPI systems. And this kind of MEPI system auto integrate the Doppler sound systems. So this is the result. Okay, if the resonance anomalous phenomena before the earthquake is true, what can we have in the space-based observation systems? So here we try to examine the satellite data associated with the Kamchatka event. Okay, what we have. This is the thermal data, the vertical profile from the thermal data. And you can see before the Kamchatka earthquake is the temperature is red, blue, red. The difference of the temperature is more than 30 degrees. So that is significant. The temperature also tells us before the earthquake, the resonance happened and is right over the epicenter area. Okay, this kind of resonance happen. What kind of mechanism can be observed? What kind of anomalous phenomena can be observed from different satellite data? This is one satellite. They majorly provide the EM anomalies. So before the Kamchatka earthquake, you can see the significant EM anomaly here, like this one. And that will be the significant difference between the ASM and the VFM. So what is that? It is a scatter magnetic and the related magnetic data. So if this kind of difference happen, that would be a potential indicator for the earthquake occurrence. So we carefully examine the data from the root of the satellite. So you can see the anomaly happened that is very close to the earthquake. And then you can see the significant difference. You can in this figure you can see the location where the significant difference in magnetic field happened. You can see the blue color here, and that is well cover the Kamchatka earthquake. So this is true. Yes, we can tell you this is true. Okay, now what is the next step? This kind of anomalous phenomena will be dominated by the resonance. So we try to think about if we can retrieve the root of the satellite. That will help us to understand where the location, what kind of where the resonance happened in the satellite data. So we not only examine the swarm data, we also take the data from the Markov size 1, and we have the consistent result. So currently we collect more than 20 different satellite data, and you can also see here. And the blue square is the location of the anomalies. And the red circle is the forthcoming earthquake within about 3 months, with the magnitude large more than 5. So I show you here, and this would be the result. You can see this is not the this is the primary works. So preliminary works. So you even though you can also find the agreement between the anomaly and the earthquake occurrence. So that means it's possible to predict the earthquake occurrence if we can understood the causal mechanism of the coupling between the lithosphere and the ionosphere. Okay, thank you for your attention. This is my talk. Thank you very much.
But then let's have Professor Kato-san's presentation first. Professor Kato, are you ready?
Yes, I'm ready.
Can you make it? Okay, now it's full screen. Yes, wonderful. Thank you.
Okay.
Right.
Thank you for inviting me. So I'll discuss about the RAC technology. So in the perspective from AI, big data, and next generation monitoring. So I'm Aito Kato from ERI, the University of Tokyo. So this is just brief my introduction. So I got PhD in the University of Tokyo in 2022, and I got PhD here, and then I got my job here from 2004. And I'm very interested in the earthquake nucleation process. For example, in the case of the flash shock sequence before the 2011 Tohoku earthquakes. Well, I'm curious about the slow earthquake phenomenon, and I'm also want to know the role of the fluid on the earthquake nucleation process. So first of all, I will start about the dense seismic observation in Japan. So in terms of the seismic and geodetic networks. So this is the two maps showing the seismic networks in the left side hand and the right hand side showing the GNSS stations. So we have a very dense seismic networks. So especially in the online section, we have a continuous data for over 25 years. And in the so I will go to the details. So for example, it's this is a real-time seismic network using the several types of the seismograms. First one is a high sensitivity seismogram. So that is called as a HiNet. So each seismometer is installed at the deep borehole, and the total number is about 700 meters. But this sensitivity is guaranteed only the period is more or less a shorter period of time. And we have many strong motion data. So the number is more than 1,000, and they're consisting of the accelerometers, so they can record the very strong motions. And we have also broad-run seismic networks. The number is not so many. The total number is 70s, but they are very sensitive, even though the long period ranges. So, and recently our seismic network is extending to the ocean, as shown by these figures. So SNet was constructed after Tohoku earthquakes. So we had already 10 years continuous seismic data. And we have also the DUNET offshore along the Nankai Trough. So this station is also operated more than 10 years. And last year we had a new ocean bottom cable network, so that is called the NNet. So NNet is already started, and we can use continuous data. So data is also open to the public. Okay, so this is some pictures showing the ocean bottom cable. So this is a sensor unit. They are deployed in the ocean floor, above the ocean floor. Okay, so this is an example of the real-time monitoring of cluster deformation. And so we had the 1,300 stations in the station network is called as a GeoNet. So it's a GNSS stations. And now recently you have also the 3 times some GNSS station, which was operated by the private company in Japan. So it's a telecommunication company. So we can use now the 4,000 GNSS stations over Japanese island. So this is some animation showing the steady deformation without any earthquakes. So without any happen over any big earthquakes. So you can see that beneath the Japanese island, the Philippine Sea Plate and the Pacific Plate is subducting. So this subduction causes a contraction into the Japanese island, except for the Kyushu island. So this international deformation of the inland arc system can be clearly monitored using such kind of the dense GNSS networks. And yeah, I want to briefly introduce about some temporary deployment of the seismometers to enhance some more density, to increase the density of the seismic stations. This is one example. So we have conducted a very hyper dense seismic deployment using the 1,000 seismic stations in the sign shares here, shown by these blue rectangles. So this is the view of these blue rectangles. This each red box showing the location of each seismometers. So this is 1,000 seismic stations. So we deployed this 1,000 seismic station to the aftershock region following the 2000 Tottori earthquakes, Western Tottori earthquakes, so magnitude 7.3. And you can see that blue dot is aftershocks, which is still lasting over 70 or 80 years. And we can get a very small earthquake. So this is a cumulative number versus magnitudes. The completeness of our catalog is close to the minus 0.6. So we have many small earthquakes. They seem to be the aftershocks following the 2000 earthquakes. And for example, this is so we can get a very highly accurate hypercenters and focal mechanisms and the B-value estimation and the velocity models using this super dense seismic networks. So this is one example of the powerfulness of our seismic network. So this is a 15 meter scale. So this is the one seismic cluster which is occurring around here. So I zoom up this very small, tiny seismic cluster. So even in the scale of 50 meters, so that is a typical swimming pool. You can see the clear alignment of the earthquakes, and this is a focal mechanism, and this alignment is well aligned with one of the nodal plane of these focal mechanisms. So we can see the very small scale structure of the consistent with the micro seismicities. We can also see some very slow migration of the due to seismicity following the major 2.2 earthquakes within this cluster. Okay. And so also we can also estimate the accurate B values and the focal mechanism, and also we can assess some criticality of the fault. So this is so one example of the focal mechanism determined by this super dense seismic networks. So you can see the many points in the focal spheres. So we can determine very, very well that this kind of the focal mechanism. So we can fix the fault geometries and source field. So, and we can also estimate B values very accurately. So we can get such kind of figures. So this is you need more cycles projected. Sorry, the B values are projected on the unit more cycle, and the low B values, so the more warmer color scale is located near the edge of the unit more cycle. So it means that the low B values for optimal fault plane directions, and that is expected from the regional stress field. So the more optimal fault plane is located is here, and they show the low B values. So using the stress field information and these fault geometries, we can also evaluate some criticality. So that is the closeness of the fault failure condition. So this is distance between the cool failure. So this is a normal stress and the shear stress. So this is a more cool more cycles, and this is a failure criterion. So we can estimate this distance from this threshold. So this is dP is the distance from this critical line. So how far from this critical point, then the vertical acceleration of the B value. So we can see some trend that the B value is a gradual decrease as the dP is getting to the close to the zero. So it means that if the stress condition is close to the critical point, then the B values also some trend to decrease. So it means that the B value is maybe the index of the fault or criticality, the failure criticalities of the fault. So B value, if the B value is low, then it means that the fault is close to the failures. So I want to move on to the next topic, that about the slow earthquakes. So that is a new class of the seismic phenomena revealed by these dense seismic and geological observations in Japan. So especially with long-term monitoring, based on the long-term monitoring. So as you know, the earthquake is a rupture of the fault. So so this is some animation drawing the ordinary state of the plate boundary. So the plate is subducting beneath some continental plate or overlying plate. Then usually they're locked. So the overlying plate is deformed, is like shown by this cartoon. And if there are big earthquakes, so the first earthquake occurs, then the overlying plate is rising up, so spring up like this. Shown by this figure, so which causes the strong motion and also tsunamis. But in the case of slow earthquakes, this flow motion is very slow. So in most cases, there is no seismic radiation during the occurrence of a slow slip. we can also we only see some caudistatic deformation of the overlying plate. So here's the map of the distribution, showing the distribution of the slow and the frost earthquakes along the Nankai Trough and the Japan Trench, and the red shade showing the location of the fast earthquakes, so it's a regular earthquakes, and blue band showing the location of the slow earthquakes. And so this is the case of the Nankai Troughs, and this is the case of the Japan Trench. So this is a main strip or fractured rupture zone by the 2011 Tohoku earthquakes. Okay, and you can see that some in the case of Nankai, so the slow earthquake, most of slow earthquake occur at the down dip side or down dip extension of the this mega rupture zone. But if you go to the west, we have a more shallow slow earthquake region, and along the trench axis, we have some spots of hosting the slow earthquakes. So there's some down dip segmentation in the Nankai Trough. So this is some summary of the difference or similarity between the Nankai Trough and the Japan Trench in terms of the geological tectonic settings. And so the plate age is quite different. So Nankai Trough is Philippine Sea's plate is more young and warm compared with Pacific plate. That is subducting beneath the northern Tohoku, so from the Japan Trench. And so the thermal regime is quite different. So the distribution pattern of the slow earthquakes is also quite different. As I explained before, in the case of Nankai, we can see the clear down dip segmentation. So here the slow earthquake region at very shallow depths, and we have a megasource rupture area at some depths, and then at the deeper depths, we have only slow earthquakes region. But if you look at the Japan Trench, there's more the down dip segmentation of slow and fast earthquakes, not so clear. We see some very active slow earthquake zone at depths about 10 kilometer or 20 kilometer shallow depths is compared with the Nankai. So this is the depth at 30 or the 40 kilometers. And in the rupture area Tohoku region, there's no clear significant activity of slow earthquakes. But in the offshore Kanto region, I'm now here, we have more slow earthquakes patches shown by this map. So in the case of the Japan Trench, the down dip segment is not so clear, but a long strike segment is very clear. And also there is some difference of the hydration state of the slab, incoming slab. So in the Nankai Trough, there are not so many, so not so significant. In the hydration of the slab is not so significant compared with the Pacific plate. So for Pacific plate, you can see the many well-developed outer rise faulting, so which could be the conduit of the conduit of the fluid into the slab region. So the hydrated state of the slab is also different. So yeah, so we are now, we don't understand the clear reason why such kind of clear difference is appears or can be observed. So it's now some topics of our research field. So if we plot the depth section of the distribution of the slow earthquakes and the fast regular earthquakes, so this is a cartoon in the case of the Nankai Trough, so the Philippine Sea plate subducting, and as I mentioned before, the megasource rupture is here, so this is a strongly local region, and we are at the down dip side, we have many families of slow earthquakes, and of course at the up deep side, we have also some spore of the slow earthquakes. So slow earthquake is a transient release of elastic energy through shear slip at a much slower rate than the regular earthquakes of the same magnitude. And slow earthquake actually is consisting of several families, as shown by these names. So I will briefly introduce some of them. So we have two major elements of the fluoroscopes. First one is the seismically detected fluoroscopes. Second one is the geodetically detected fluoroscopes. So the seismically detected fluoroscopes, the low frequency earthquakes and tremors, and the very low frequency earthquakes. So there are some time scales of the duration of each event. So this is a seismically detected fluoroscopes. And in the case of a geodetically detected event, we have a short-term short-slip event. So duration is 1 week, and long-term short-slip event is the duration is years or months. Okay. So yeah, so they are occurring. So they are the intermediate type of short-slip. That is the transition between the first rupture of regular earthquakes, so strong lock region, and stably sliding more deeper or more shallow interface. So earthquakes is a phenomenon of occurring in the transitional zone between the locked and the stable sliding region. And there are many kind of phenomena. And they have so many characteristics, diversities. So so this is a cartoon showing the more three-dimensional view. So in the Nankai Trough, as I mentioned before, in the center, in the middle part of the plate boundary, we have a locked region, and deeper and shallow depths, we have a thoracic region. But in the case of a Japan Trench, it's more complex, and the thoracics mainly occur in the little bit shallow depths, and we can see the clear long strike segmentations, and in some parties, the thoracics and the first earthquake occurred very nearby each side, very close to distance, so they are interacting very strongly. And so there are some clear difference of behavior of a slow earthquake and a fast earthquake between the Nankai and the Japan Trench. So after the discovery of slow earthquakes over 20 years ago, now the slow earthquakes have been discovered around the world. So not only Japan, so in Taiwan also we have some slow earthquakes, also in New Zealand or some countries along the Pacific Rim, and these earthquakes are closely located to the big earthquakes, of course. So they are located nearby. Okay, so there are some interaction between the slow and the fast earthquakes. So, but we don't understand the full spectrum of the interaction. So it's a very current research topic. So using this data set collected over 20 years, so this is a diagram showing the duration of each slow earthquake event versus the seismic moment. So this is a magnitude, and so the first regular earthquakes follow this scaling, as you know. So the duration is increases with the seismic moment. So 1/3 of the seismic moment if the stress drop is constant over the magnitude. But most of the earthquakes plotted on this trend. So you can see, so these blue or red shades showing the slow earthquakes discovered around the world, including Japan. And this broad major trend can be characterized by this equation. So the duration is proportional to the seismic moment. Okay, so using this duration and the definition of the seismic moment, and if the displacement is constant, then the length of the thoracic region should be increased proportional to the square root of the time. So it means that is a diffusion process. So we expect that the underlying physics in thoracics is maybe diffusion process. So it means that the thoracic should be more ubiquitous or universal because the diffusion process can be observed in more frequently in nature. Okay, so I will also introduce about the AI for modeling of fast and slow earthquakes. Here in recently, So this is one of the workflow to detect the fast earthquakes. So we prepare the data, and so it's a continuous seismic waveform data. Then we apply the phase pickers, such kind of the very famous one is the PhaseNet. So it's based on the deep learning, so CNN models, and we can get the P and the S peaks. Then we did the association to get an event. Then we locate the earthquakes, and if we want to get a more precise hypercenter, we can apply the relative location methodology to get the precise hypercenters. So the PhaseNet is based on the unit architectures, and so this is an example of the picking of the P and the S wave. So you can see that this is a 3-component seismogram. So this is the vertical, and this is the horizontal component. You can see the very clear P arrivals here, and S arrival here in the horizontal component. And blue and red is a manual pick, so it's labels. And this is these are probabilities output from this PhaseNet architecture model. So you can see that the peak of the probability is almost correspond to the onset of the time, of the picking of time, of the human picking, P and S wave. Okay? So this is a residual, so time residual between the automated and human level P and S wave peaks. And the difference is very small, and also the narrow residual of P peaks, because the P wave arrival is more sharp, more clear compared with S wave. Okay, so using these models, so this is one example. Apply this model to the ocean bottom cable network in Japan along the Japan Trench, shown by these lines. And so this is the magnitude versus time, and so this is our red dot showing the newly detected event using this workflow. So more smaller event detected in the offshore, especially southern region, so region 1 and region 2. So this is a region 1 and this is a region 2. And you can see that much more smaller event can be detected in the region 2. So region 2 is more far from the on-land seismic station. So it's very difficult to locate smaller earthquakes from the only using on-land seismic station. So now we have a ocean bottom cable. So ocean bottom cable can enhance our detections, as shown by this cartoon. Also, they significantly improve the depth accuracy of the hypercenter, shown by these two figures. So this is so without any ocean bottom cable, you can see the hypercenter is getting very deeper. But if you include the ocean bottom cable data, then they are very well fixed, and they follow the almost top of the seismicity, follow the subduction of the Pacific Plate. Okay, so yeah, we have many interesting features. For example, you can identify some forward seismic belts shown by this cartoon. So earthquakes are more concentrated at the foreshock side here, so which is originated some earthquake clusters in the subducting slab. So there's some fluid maybe fluid is such a trigger, such kind of the concentration of the seismicity in the hanging wall, in the forward side bed. Okay, also we can also apply the machine learning technique to identify the tremors. So tremor is one of the slow earthquakes family, and we developed some machine learning methods, so using such kind of architecture modeling, and so this model automatically classified the seismic event to the earthquakes and tremors and noise based on the feature of the spectrum of each seismic event. And after extracting the tremors, we apply the station association based on the graph-based clustering method. So in this case, we can find the 3 clusters. So and based on this clustering information, we can locate each tremors using the envelope cross correlation method. So in this time window, we can collect the 3 tremors at this almost same time window. So applying this method and extend analysis to 2016, so roughly 10 years. So this is an epicenter map of detected tremors. And as shown before, the tremors are located as shown by here, and they're in the rupture area of the Tohoku region. We have no tremors, but surrounding them, yeah, okay, tremors are surrounding them, and this is a long activity of the tremors along the Japan Trench. So you can see there's some clear migration during the major episode of these activities. Oh, and if you look at the more details in space and time, we can see the very clear migration tremors. The migration speed is about 10 km per hour or 5 km per hour. So that is a typical migration speed of the slow earthquakes. Okay, so we also developed some machine learning detection of the slow slip event. So slow slip event also the one of the family of the slow earthquakes. Through joint analysis of seismic and geodetic data. So we use seismic station data and GNSS data. We combine, actually we used seismic features as a teachers to get some slow slip event. That was recorded in the GNSS data. So I don't have enough time, so I will skip details, but this method, so we can combine the seismic and geodetic data to enhance the detection of the small slow slip event, especially the more smaller magnitude slow slip event. So there are some very clear example detected by our method. So you can see the clear pattern of the slow slip event. Yes, so applying this method, so we expect that we can get more smaller slow slip event compared to the previous studies. Okay, finally, I just briefly mention about dust measurements. So as a new sensing technology for earthquake modeling. So there are many studies about earthquake modeling, especially, of course, in Taiwan, but in the world. So, but I just mentioned about our project. And so, as you know, that is a technology that uses optical fiber cable as a super dense sensors to detect seismic vibration along the fiber cable. So we now conducting the dust experiments or dust monitoring in the Turkey, so Marmara Sea, the eastern part of the Marmara Sea. So there is Istanbul. So Istanbul is facing the North Anatolia Fault. So especially this is called the Princess Island segment. So which is expected to be the big earthquakes in futures because there's a clear seismic gap in this section. So we now doing the seismic monitoring using the dust here. So this is the cable geometry we used here. So we analyze the dust data from local and regional and state seismic events shown by this figure. So this is an example of the local earthquakes. So you can see the very clear P and S wave arrivals. They are almost seamlessly continuous. But in some portion, you can see there's some scattering of the S wave. So it may be related to the fault structures. And also, if you look at this P and S wave, this record from magnitude 3.8 earthquake, you can see clear low velocity, so the delay of the P and S wave arrivals. So this delay arrivals indicate that there's some low velocity layer just beneath the North Anatolia, just southern side of the North Anatolia fault. Yeah, so using this dust data, we can also locate the earthquakes. For example, so this is some beam forming of some earthquake waveform. So you can see that some waveform is coming from the southern part. And we divided this for optical fiber cables to small segment, and for each small segment, we can beam forming, so the location of the earthquake sources. Then we stack the all energy. Then this is the result. So you can see the highlighted region by this warm color. So this is the location, the peak of the energy. So this is the location of the earthquakes. So actually, this earthquake occurred detected by the regional seismic networks, and this is a Qatar epicenter district location. So it's almost nearby. So using this method, we can enhance the detection of the small earthquakes near the ocean, this fiber cable. So this is a targeted earthquake epicenters by the catalogs, existing catalogs, but there is no seismicity in here. But we have many small earthquakes near the dust cable, so our method can detect the more small earthquakes near the fiber cables. Okay, so that is summary of my talk. So the dense seismic and geologic observation networks have transformed our understanding of earthquake processes across a wide range of spatial and temporal scales. And observation from these networks reveal the diversity of slow earthquakes and their close relationship to megathrust fault behavior and stress accumulation and fluid release process. Recent advancements in AI and machine learning are enabling rapid and high precision detection of both burst and slow earthquakes from massive seismic and geologic dataset. And thus, using fiber optic cables is opening new opportunity for ultra-dense monitoring in offshore and urban environment where conventional observation are limited. The integration of big data, AI, and next generation sensing technology will play a key role in improving earthquake monitoring and understanding earthquake physics. Thank you for your attention.
Yeah, thank you so much, Professor Kato. That is a very interesting talk and excellent talk. Any question from the audience? I mean, for me, you know, maybe I ask the first question. That is, am I correct in saying that there's no overlapping between the slow quick and fast quick areas? So why is that?
Yes, so you mean that no overlapping? Yes, so they are close to by each by,
Yeah,
because
but there's
yeah.
no overlapping. I mean, they kind of
Yeah, because slow earthquake phenomena is some intermediate time. So the earthquake occurred in the very strong locked region. And yeah, slow earthquake is some intermediate fault slip type between the very strongly locked, so the rupture of the brittle rupture of the locked region and the stable sliding region. So stable sliding means that there is no accumulation of the stress without any locking of the fault. So slow earthquake is a kind of the phenomena is the intermediate between the brittle failure and the stable creeping behavior. So yeah, there is some transitional behavior. So they are not overlapping, maybe.
It's still next to the quick area, right? I mean, they're
next to each other. Yes.
And even though it does not cause damage, but still, you know, right. And also that the slow quick area is in the coastal region. Is it near to coastal region? I mean, for the Nankai Trench,
yes.
a trial.
Yeah.
And whereas
right.
the bigger flux, okay, yeah, right.
Yeah, for example, if you go to the northern part of Tohoku Oki region, here the slow earthquake region and the regular earthquake region is overlapped each other already it's overlapped. So but if you look at the details of the epicenter of the slow earthquakes and of regular earthquakes, they are not overlapping actually. If you zoom up, they do not seem to be overlap. So there's some difference of some fault properties or actually for the geology. So we don't know the exact reason. So it's now the hot topic. Yeah. But very interesting. Yeah. So in the Nankai case, it's more big scale. So even the large scale, so we have a very clear segmentation of that. Slow and fast earthquake. But in the Japan Trench case, especially here, so Sanrik Oki, so we have more cross, they are close to each other. Yeah.
But they're studied mostly by your monitoring. Fiber optic, is that we call fiber cables monitoring system?
Oh yeah, SNet is yes. This is coming from the SNet. So as I mentioned here, so it's not fiber, not dust fiber. Yeah, it's each symbol is a location of the station, seismic station, or pressure gauges. Yeah.
How far from coast you go? 500 kilometer or what?
How far from coast, you mean?
Yeah,
Coast?
yeah.
Okay.
You
From here.
or to the seabed, right?
Okay, here to here is about 250 kilometers. Here to here.
Okay.
Yeah, less than 300 kilometers.
I wonder if we have that also in Taiwan. That would be nice to have. Yeah.
Yeah, so yeah, SNet or such kind of ocean bottom camera is very powerful to understanding the earthquake seismicity or through earthquakes more precisely.
Right.
Yeah. Yeah, some tremors or some small earthquakes cannot be detected using only land station, especially near the trench. Yes, activity near the trench. It's very hard to detect such kind of the activity. So they are very, very useful to know the whole picture of the seismicity.
Mm-hmm. And the picture, in the bottom of your
Yeah.
Is that that's how you put the monitor, right?
What do you mean? What?
I mean, those are instruments you put into the seabed. Those,
just dollop. So it's a cable. So it's connected to the long cable. Yeah, there's a long cables. It's connected to the long cables. So using the SIP, we just drop this sensors and the cables. Most of part is the cables. Ocean cables. So they are connected to the cables. So it's better, maybe if you look at this map, is more better. Sorry. So this is a cable. Sorry. Black is a cable.
Oh, okay. All right. Okay.
These are stations. So there are some part is connected.
Is it hard to maintain? I mean, do they broke down?
Yeah.
Kenji, are you still there? Kenji? I mean, I want to ask him whether Taiwan is doing that or not. It sounds very interesting. Okay.
Yes, I'm here. Well, I have to leave soon, but I'm here. Yes. Well, actually, Taiwan has a similar cable, and I don't know for the seismograph, but pressure sensor is there, and that detected like a foreign earthquake, tsunami, and also the Kamchatka tsunami is detected. Yeah.
How many stations are there in Taiwan?
I think there's about 10, but now I think only half is operational. The other half seems to be broken. Yeah.
Oh, broken.
Broken. I don't know for some reason, but I don't.
For some reason, I don't know. What?
CWA has a Central Weather Agency or Bureau. They have such similar system. Yeah.
Okay, great. Other questions?
I have a question.
Please.
Yes, please.
Yeah, maybe just a suggestion. Firstly, comments. Very, very wonderful and great. Very good presentations. Okay, thank you very much for your presentation. And then my suggestion is that if you notice that the earthquake inactive with subduction zones, and the earthquake active in collision zone, land collision zone. For example, the 30th from Turkey to Pacific to the Malaysia or Indonesia, like that. The 30th there. The comparison of the earthquake process. Is there any consideration about the comparison of the different subduction zone and collision zone in land collision zone from Turkey to Indonesia? Okay.
So you mean the comparison study of the
yes.
regular earthquakes or slow earthquakes, both?
Maybe also the slow earthquake maybe is common phenomenon, especially before the big earthquake or great earthquake. So with your AI or machine learning techniques, if we can get more information of the land collapsing zone, not only subduction zone. Okay.
Yeah, so first point is you mentioned about the it's interesting to compare the seismicity especially in the worldwide scale. So of course we are already some studying about slow earthquakes and big earthquake around the world. So we have similar especially in the terms of slow earthquakes behavior, we have see the similar characteristics between Japan and other countries, and also big earthquake also similar. But there are some slight differences. So it's an important point to understand what's causing such differences. And about the second point you mentioned about, so the slow earthquakes sometimes occurred before the big earthquakes, so not always. So so the slow earthquake itself is not yet so powerful to predict the earthquakes, especially in the timing. So we are now still we are trying to understand what's going on, especially the interaction between the slow earthquake and the fast earthquake. So it's under study, under working. We need more data. And we need to deepen our understanding about the interaction between the slow and the fast earthquakes. So, but they are occurring very close to each other, as we have already discussed in the early part. So there is some hint, but it's not so easy. Yes, it's not so easy. So
Okay.
thank you very much.
The time is up because it's almost 12:30, and I thank you so much, everybody. And maybe I should invite Professor Kato for another talk in future. So we are thinking about having the next series of webinars maybe in 1 to 2 months time. And as you can see, today we have a couple of things to note. The first, it's very good to have such a review talks, 45 minutes long, for our expert to explain the very new developments and complementary maybe to each other, and also that by comparing, we gain a lot of new insight. Important things that our experts are coming from places with advanced research in seismology and earthquakes. So we hope that their knowledge, their experience, or their observation could be applied or so to say to be brought to the other countries which don't have such advanced facilities or advanced programs yet, and hence to generate regional cooperation. And I hope that this will be accomplished sooner or later if we keep on doing this. And I want to thank therefore Professor Fu Chang Huang for organizing this working group, and I also want to thank Professor Takehiko Sato for attending this meeting. And I hope that because of that, he would support our activity in future. And if you have any questions, please, write to us. Then we could pass on to the speakers. And thank you so much, and have a nice day. Thank you. Bye bye.
Yes, and keep contact. Yes. Okay.
ありが
Bye-bye.
とう。
Keep contact.